While realizing the current mirror, we have encountered this structure, the basic drain feedback structure, where the drain voltage is fed back to the gate. Okay. Now this structure occurs quite often, so let's spend some time studying this. Now the MOS transistor has 3 terminals. Okay, and with this connection you can think of that as a 2-terminal element. Okay, so I could put this MOS transistor in a box and bring out only 2 terminals, and one of the terminals is connected to both the drain and the gate. Okay, now if we think of this as a 2-terminal element, and let's also make our usual assumption that the threshold voltage is positive, so this structure will be either in saturation or cut off completely. It cannot be in triode region, because if it has to be in the triode or linear region, VDS has to be less than VGS minus VT, but we have VDS equals VGS, so this is not possible for positive threshold voltages VT. Okay, now let's just plot the IV characteristic of this element, thinking of it as a 2-terminal element. We have the voltage V and the current I. Okay, what happens is that if I do plot the IV characteristic, and I'll plot it only for V greater than 0, because our model of the MOS transistor is valid only when the voltages are greater than 0. Okay, so let's say 1, 2, 3, 4 volts, and I'll consider the same transistor as before, where mu and Cox W by L is 100 microampere per volt square and Vt is 1 volt. So it's pretty obvious that if this voltage V is less than 1 volt, no current can flow, because VGS is smaller than 1 volt and the transistor is cut off. Okay, and beyond that, because it's in saturation, it follows the square law equation, which says that I equals mu n Cox by 2 W by L VGS minus VT square. In this case, I is this current I, the ID is basically this current I, and VGS is this V. Okay, so it follows the square law behavior. Okay, so at VGS of 2 volts, it will be 50 microamperes. So let's say this is graduated in microamperes. At 3 volts, it will be 200 microamperes. At 4 volts, 450 microamperes, and so on. Okay, so these are the IV characteristics of the transistor, and this, you recall, is reminiscent of the diode. Okay, the diode also had some characteristic where there was a very small current here up to some point, and after that the current increases. Now in case of the real diode, it increases exponentially, whereas here it increases only as square law, but this can be in a way thought of as a 2-terminal element, which is the diode. So this connection is known as diode connection, or this transistor whose drain and gate are connected together is known as a diode connected transistor. Okay, so you encounter this in many places. You have this characteristic, it can be used to obtain a certain voltage drop, or it can be used to obtain certain bias voltages and so on. Now the incremental picture of this we are already familiar with. We calculated it while analyzing the common source amplifier with current mirror bias. So it will have certain operating point I and V, and around that operating point, what will we have? If you write it in terms of the small signal model of the MOS transistor, this is the gate, drain and source. This is VGS and this is GM VGS. Okay, and the gate is connected to the drain. Okay, so now between these two terminals, either gate source or drain source, it's the same. This is equivalent to a resistor of value 1 by GM. This we already know, we have analyzed it. If not, you apply a test voltage here and see what current flows, take the ratio, you will find this. Okay, so a diode connected transistor has an incremental equivalent, which is a resistor value 1 by GM, and GM has to be evaluated at the operating point. Okay, and you can also include the output conductance of the transistor in saturation region. If you do include that, what happens is that appears in parallel with this one. Okay, this will have a resistance RDS, which is the reciprocal of the conductance GDS, and the whole thing will be equivalent to a single resistor of value 1 over GM plus GDS. The conductances add because they are in parallel. Okay, and this is a useful result to remember. You do encounter the diode connected transistor in a lot of situations in electronic circuits, and it's useful to know its large signal and small signal behavior. Okay.